Good morning, good afternoon, good evening, everyone. Today we are going to be discussing about introduction to absorption spectrum, which you are going to carry out the lab. Okay, so we already explained the concept of absorption spectrum when we were discussing about Beer's law, Lambert's law. So this video is going to be like a build-up on the previous lecture. So we already defined absorption spectrum, which we said is a graph or an illustration that relates absorbance to a wavelength of a particular substance. So when we have a plot of absorbance against wavelength, we said we have an absorption spectrum. And we have explained that so many compounds, they have their own characteristic absorption spectra in the UV or visible region, and we can actually identify this substance in a mixture. So it's not all compounds or all substances that have characteristic absorption. So we discussed about proteins. We said they can absorb light strongly and they have this absorption maxima at a region of 280 nanometer due to the aromatic amino acid that are found in the protein. And so we observe a peak where they strongly absorb at 280 nanometer. So also nucleic acid, they have absorption maxima. They absorb due to the presence of that aromatic nature that is found in the bases, that is adenine, thymine, guanine, cytosine, and uracil. And they have absorption maxima at 260 nanometer. Okay, so there are other substances or compounds that do not absorb. For example, sugar or glucose, it does not absorb. Okay, so we also have a uric acid, which has an absorbance maxima, or it absorbs maximally at a region of 293 nanometer at pH 9. So this uric acid, when it's converted or oxidized by an enzyme called uricase to allantoin, when you take the absorbance of that allantoin, you will see that at that wavelength, 293 nanometer, it does not absorb. So when uric acid is oxidized by the enzyme uricase to allantoin, there is no absorption at that wavelength. But when it's in its intact form, the uric acid without any action of any enzyme on it, it can absorb at 293 nanometers. So you can see from this black chart is for the uric acid, which has highest peak at 293 nanometers. So it's possible to actually carry out an estimation to measure the activity of this enzyme uricase. Or also you can also quantify the amount of the uric acid that is present, because you will have to carry out the absorption spectrum to see whether there is this peak, there is absorption at this region maximally. So we can say we have our allantoin and we have our uric acid. So if there is presence of this enzyme, and under the condition that the enzyme can catalyze uric acid to allantoin, we can actually say detect the activity of this enzyme by measuring the absorbance of uric acid in the solution before the reaction and also after the reaction. Before the reaction, you will observe this peak at 293 nanometer, but after the reaction, because you have allantoin, you will not have this absorption because the uric acid has already been converted to allantoin. So also we have these coenzymes NADPH and NADH. These are coenzymes that are required by some enzymes, and we can say that the reduced form, we have NADPH. The one with H is the reduced form, and NADP without H is the oxidized form. So the reduced form of NADPH and NADH as coenzymes required by some enzymes to carry out their activities, we can see a maximum absorption at a region of 240 nanometer. Okay, they have absorption maxima at 340 nanometer. So the oxidized form do not have such absorbance at 340 nanometer. So we can say enzymes that require these coenzymes, we can monitor their activity by either the utilization of this NADH and NADPH, okay, and also observing the absorption maximum before the reaction if the enzyme is present, and detecting no absorption maximum at that region after they must have been oxidized. So we can also try to estimate or quantify the activity of such enzymes that required those coenzymes. So we can also see there is absorption maximum, the shift of absorption maxima that is being observed when hemoglobin, you can see the normal chart here, when hemoglobin is intact, there is no alteration in the structure of the hemoglobin. We can see a highest peak that is observed here, okay? So when we have carboxyhemoglobin, that is hemoglobin with carboxyhemoglobin, that's hemoglobin that is having CO attached to it, right? So we can see there is absorption maxima shift in the, which is not normal, okay, because it's not the intact hemoglobin. So also we have oxyhemoglobin. You can see the chart is different from that of carboxyhemoglobin and also normal hemoglobin. So when this is a modification of the hemoglobin, we have oxyhemoglobin, the hemoglobin that has oxygen attached to it, ready to deliver. Okay, so we have, when we take the absorption spectrum, we'll see there's a shift in the normal absorption observed by the normal hemoglobin. So also we have methemoglobin. Look at the absorption chart. Look at it. It's a little bit different when you compare with all the rest of the three. This methemoglobin is the dysfunctional form of the hemoglobin, because in methemoglobin, you have iron in +3 oxidation state rather than the +2 oxidation state that is found in the normal hemoglobin. That is methemoglobin. So all these charts, they are telling you that this substance, these compounds, these molecules, they have absorption maximum. They have a region where they can absorb light maximally. So any alteration in that means that you are not dealing with the intact molecule. So in today's experiment, we are going to be determining the absorption spectrum of the two dyes. We have methyl orange and bromophenol blue. So we are going to use these two dyes to carry out our experiment. And this experiment is going to be in 4 stages. The stage 1 is to determine the absorption spectra of the two dyes, that is bromophenol blue and methyl orange. And in the stage 2, you are going to carry out the determination of absorption spectrum of the mixture of these two dyes. So you now mix the two dyes, bromophenol blue and methyl orange, together, and you determine the absorption spectrum. The first one is to carry out absorption spectrum for each of the dye. And the second one, you mix the two dye and carry out the absorption spectrum. That's 2. Then the third stage, you are going to carry out the, you determine the absorbance of solution that is containing different concentration of these dyes. So you have bromophenol blue, different concentration. You have methyl orange, different concentration. So you are going to calculate, you are going to measure the absorbance of these different concentrations of this dye. So you have now different concentration, you have absorbance for each of the dye. So what are you going to do? The next one is the 4th stage, which you are going to do calculation for each of the dye, the concentration of each dye that is present in the the different concentration that you have for each of the dye, bromophenol blue and methyl orange. So when you have different concentrations and you have absorbance values, what do you think you can do? You can plot a calibration curve. That is to say, you have a standard curve where you can use to extrapolate the concentration of the unknown that is going to be given to you. So in this experiment, I already have values here for the absorption, absorbance at different wavelength for these two dyes and the mixture. So we have bromophenol blue and methyl orange, and also the mixture of the two dyes. So at 400 nanometer, this is wavelength. You can see at 400 nanometer, we have bromophenol blue, we have 0.21 absorbance, 0.33 for methyl orange, and 0.33 also for the mixture of the two dyes. So also at 450, we carry out the absorbance, taking the absorbance for the two dyes and also the mixture up to 680 nanometers. So this values is going to be useful in plotting the absorption spectrum for each of these dye. So we have now wavelength, we have absorbance. So we have absorbance against wavelength for bromophenol blue, absorbance against wavelength for methyl orange, absorbance against wavelength for the mixture of the two dyes. So we are going to plot absorption spectrum for the three dyes, that is to say the two dyes and also the mixture in the same axis. On the same axis, you are going to plot it on the same axis. So what you are going to do is you now scale your axis. You choose a suitable scale, because look at your values that you have here. You have the wavelength, which is going to be on the x-axis, okay, and you have the absorbance, which is going to be on the y-axis. So you check the smallest value you have on the x-axis, you check, all right, and also I think it's around this 0.16, and the highest that you have, you check also. Sorry, we have 0.01, so you take note of that. 0.01 is the least value, and also we have the highest value, which is 0. I think 58. Yes, okay. So you take note of that in constructing your scale so that you have a good plot. So we already did that. We have a graph of absorbance against wavelength, which is called absorption spectrum. And we have chart here and legend that explain this blue is for bromophenol blue, methyl orange. Look at this. This should be orange color, right? And we have a mixture of the dye, which is in gray color. So what we did here, we plotted our absorbance on the x-axis. Very important, you should not forget element to level your graph. Each graph you plotted must have a title, the axis must have their corresponding title and also unit where applicable. So we have, this is our x-axis. Okay, we have from 0, 0.1, 0.2 up to 0.6, and we started our x-axis, which is the wavelength axis, with from 300. So 300, 350, 400, 450 up to 700. So we plotted for each of the dye. You remember, you have at 400 for bromophenol blue is 0.21. So bromophenol blue, look at it, at 400 is what? 0.21. So you plot it. It's very important to have that plotted appropriately. So when you did that, you will join the axis, you will join the points, use freehand sketch. You are not going to, don't use a ruler to say you must have a straight line. No, just use freehand sketch to because it's a chart, absorption spectrum. It's not going to give you a straight line. So you join all the points together. So also for methyl orange, we do the same thing. For the mixture of the dye, you do the same thing on the axis, on the same chart, on the same axis. Okay, so you have three graphs together. So you see here you have the absorption maxima for this mixture, for methyl orange, and also for bromophenol blue. Very important. So that's the first stage. Then you did the first and the second stage, which you determine the absorption spectrum for the mixture of the dye and also in the invisible dye. So for the second, for the third experiment, or the third stage, you are going to carry out the absorption. You are determining the absorbance of solution containing different concentration of dye. So So for you to do that, you need to calculate the concentrations for each of the dye. For bromophenol blue, if you look at your manual, practical manual, the concentration, the stock concentration is 100 milligram per liter. Okay, it's 100 milligram per liter. So if 100 milligram is present in 1 liter, that is 1000 milliliter. How many milligram will be present in 1 mil? So you have 0.1 milligram per mil. Okay, so you do the same thing. 100 milligram is present in 1 liter. How many milligram will be present in 2 mil? You remember that you were given a stock of dye and you are given 1 mil of dye. You add it 1 mil of dye, 4 mil of water, 2 mil of dye, 3 mil, 4 mil or 3 mil of dye, 2 mil of water, and 4 mil of dye, 1 mil of water, and 5 mil of dye without adding any water. So that is where we have this calculation. For the tube that has only 1 mil of the water, only 1 mil of the dye, that is tube 1, okay? You have 100 milligram is present in 1 liter. How many milligram will be present in 1 mil? That is 1 mil of the dye from tube 1. So also here in tube 2, 2 mil of the dye, okay, from your table in the manual. Then for tube 3 is 3 mil of the dye you've taken. So you have 0.3 up to 0.5. Okay, so this is important because you are going to take the absorbance for each of these tube. You pour the content of this dye inside the cuvette and you take the absorbance. Okay, so you have for tube 1, this is the milligram per tube that you have. You have 0.1 up to 0.5. We have already calculated it here. So for the absorbance that you have, for each of the tube, you pour the content inside as a cuvette and you measure the absorbance at 580 nanometer or any wavelength that is suitable for the experiment. So you have your absorbance that you recorded for tube 1. This is for tube 2 up to tube 5. So what are you going to use this for? You are going to plot a graph of absorbance against the concentration of the dye per tube. So this is what we call the calibration curve. When you plot the absorbance against the concentration, you have your absorbance values here, and this is the concentration, so in milligram per tube, okay? So you have a straight line. Remember, absorbance is directly proportional to the what? Concentration according to Beer's law or Beer-Lambert law. So if you look at it, can we say there is direct proportion between absorbance and concentration? Yes, we can say, because you can see a straight line here fitting almost all the points. Okay, as the concentration increase, you have an increase in the absorbance. Okay, so that is for bromophenol blue. So for methyl orange, the stock concentration is 10 milligram per liter. Okay, so 10 milligram is present in 1 liter. How many milligram will be present in 1 mil? You remember. So also for methyl orange also, you have tube 1 up to tube 5. Okay, so tube 1 is 1 mil of the dye, 4 mil of water. Tube 2, 2 mil of the dye, 3 mils of water. Up to tube 5. Tube 5 is 5 mil of the dye, 0 mil of the water. So you have your entire tube containing the dye. So when you calculate that, you see that you have 0.01 milligram up to 0.05 milligram. Look at it. 10 milligram is present in 1 mil, in 1 liter. That's 1000 mil. How many milligram will be present in 2 mil of the dye? So when you cross multiply, you have what? 0.02 milligram per mil. So also you take the absorbance. This is for tube 1. This is the milligram of dye that you just finished calculating, and you have your absorbance that you have taken for methyl orange also. So for tube 1, you put the content inside cuvette and you measure the absorbance. This is what we've gotten up to the 5th tube, which is the last tube here. So also you plot a calibration curve, absorbance against concentration. You have absorbance on the y-axis and concentration on the x-axis. So look at it. Is the absorbance directly proportional to the concentration? Yes, similar to what we've seen in the bromophenol blue plot. So I think this quick explanation of what you are going to do, and what you are going to be expected to have at the end of the day. And I think we are going to stop here. I hope you really enjoyed the video. Thank you. See you next.